Hi, I'm Alex Spafford, the head of the Merlin Neurotechnology hardware team. We've been hard at work over the past semester developing our very own EEG acquisition board, and today that's what we're going to show you.
The main purpose of the acquisition board after the signal is acquired is to filter out unnecessary data. For our purpose, low-pass, high-pass, and band-stop filters were used. Low-pass filters are used to filter out unnecessary frequencies that are greater than beta waves, so above 30 Hz. High-pass filters are used to filter out unnecessary frequencies that are less than alpha waves, so below 12 Hz. Then the band-stop filter, otherwise known as the notch filter, removes frequencies that are at a single frequency or range of frequencies. In our case, notch filters were used to eliminate 60 Hz signals. This is because power lines create a lot of noise at 60 Hz, and so would have a large effect on the data if it wasn't removed.
So using the information that we have gained about filters, what we then need to do is create the schematic for our EEG acquisition board. So what we are mainly focusing on is the filtering and amplification of EEG signals. And so what we can see on our board is that we're starting with an instrumentation amplifier. So an instrumentation amplifier, which is here, is connected to the screw terminal, which is where you'll input the electrode signals, which is then multiplied. The signal is multiplied by some gain, which is determined by this resistor R3 here. So what an instrumentation amplifier, one of the main things it does is it takes the difference between the voltages of the two lines, and then using a gain equation, which is set by the type of amplifier you get, like the model, and then the gain equation that is set out on its data sheet, you will end up with a gain equation which will be usually 1 plus something divided by that resistor. So the smaller the resistor, the larger the gains. We've chosen a resistor of 560, which gives us about 90 gain. And then moving on from there, we just see our series of different filters. So as discussed by Claire earlier, was that we have our notch filter here, both for 60 Hertz. And then we have our high pass filter, which is going to be 7 Hertz, so that everything below those alpha waves gets filtered out. Our low pass filter here, everything above the beta waves getting filtered out, and then another high pass filter to make sure all those low frequencies that we don't need are gone. One design problem we encountered was the fact that 25 nanofarad capacitors are very hard to find, or at least not easy to find cheaply. And so for this low-pass filter, we wanted a 25 nanofarad capacitor, but instead what we did was put 4 capacitors in series. So this divides the overall capacitance by, or that initial capacitance of 0.1 by 4, giving us a 25 nanofarad capacitance in the end, which allows us to achieve that low-pass filter that we want. Looking over here, we have a potentiometer which allows us to alter the gain provided by this amplifier. And so by varying it from low to high resistance, what we do is be able to get the gain from low around 80 to up to about 450, which really allows us to get that signal in our desired range of just below 1 volt for our circuit. Then as we see here, this terminal from this screw, that's where we have our one output, and then the other output will be connected to ground because we want that voltage difference. And then we have our power lines here and here, and that's our overall schematic. So the next part of the design, once you have the schematic, would, in theory, to be building it on a circuit on a breadboard with all your components, and then making sure it works. But so before you can do this, you actually need the parts. So what you do is in your schematic, you can get this footprint editor. And so for each capacitor and resistor, what you'll need to do eventually for your PCB is have the exact dimensions of every part you need laid out onto the PCB. And so by going through on a website like DigiKey, figuring out all the parts you're going to order because you're going to want to be testing on the breadboard before you fabricate your PCB, you can order all these parts, input the dimensions of the parts, and get it all ready to make your PCB. And then you'll end up going and building it on the breadboard, testing it, making sure it works, and then comparing that back with your schematic if you need to change anything. So we're using KiCad, and it has this really helpful footprint editor where you have a lot of already inputted data, like so that you don't need to hand enter all of it, and it'll, depending on the capacitor, it has normal dimensions that you will probably end up using, and it makes it very easy. But so as you can see, these are our different amplifiers, then we have all our resistors, screw terminals, and capacitors. And it's all laid out with the pin length or distance between the pins, and then the length of the pins, the diameter of the capacitors, and then here you have length of pins and length of resistor and stuff. So the last part, once you have tested all your parts, built your circuit on the breadboard, made sure your schematic works, is creating your PCB. And so this is our PCB design made in KiCad. And so as we can see, this is the start where our screw terminals are. This is the power and the output screw terminals. Then each of these is a capacitor, resistor, and each of these is our amplifiers. So when you're designing this PCB, what you're trying to do is make sure that, as you can see on ours, we have these red lines and these green lines. So each of those is connections between 2 points on one side of the board or the other, red representing the top side of ours and the green representing the bottom side. And so what you want to do if you're designing your own is making sure that you arrange all your parts so that there's as little overlap between lines, because if there's too much overlap, then you need to, and you can't design it can't connect to the components in a way that you're going to need more than two sides. Then you end up needing to implement vias, which flips the side that the trace is on, the green and red being the traces, and this starts ending up making your board take longer to fabricate, as well as upping the cost. And so the overall goal is to make the connections as simple as possible, because it can only cross over the other colors and not itself. So if you somehow cut off half your board with the red traces, then red traces won't be able to get to the other half, and you'll need to end up implementing vias. But so this is our PCB. It is about 10 by 6 centimeters long. 10 by 6, and this is what we ended up submitting to Osh Park to get fabricated, and what we ended up using for our board. So for our final PCB that was produced and then soldered together, what happened for a little bit was, for one, all these wires. So here and here we were supposed to have screw hole connectors, but the wrong parts were actually ordered, so it didn't fit into the slots of the PCB due to the pin spacing, so wires had to be soldered on instead. But other than that, it went as intended, and as we can see, right here is the instrumentation amplifier with these two inputs here have traces connecting to the pins, so that allows, these can connect to our electrodes, giving us that input. Here's a ground pin that we have to connect to a breadboard, so that any the electrode or the sound card, anything that needs to be grounded, can also be grounded at the same point, the same reference as the board. Then we have our positive and negative 9-volt terminals here, and then our output port here from the circuit, which will then be that plus the ground is the difference. So as we can see, we have our, right here, the capacitors talked about earlier that had to be all four implemented to create that capacitor dividing to allow for the 0.25 nanofarad, and then the rest of the circuit is just seen as present. So for our project, what we did for the transmission, real-time visualization, and data recording components was use an open source code base called processing. And so once our signal was acquired and then processed through our filters, and then transmitted through the aux cable to the sound card of our computer, it can be visualized through the processing program. And so the code we used is given credit for in our repository on GitHub, and it is open source code that can be used to visualize EEG data, either from an Arduino or from the sound card itself. And so we use this to get the data, as well as processing can be used to save the data, which isn't implemented into the original code. So if you go on Processing's website, they provide these basic saving tutorials as well as code, which allows you to, when you either press a key, click your mouse, it will save the data that you're streaming. And so as you can see on the screen, you have the sine wave up at the top that is the brainwave data, and so this can then be saved afterwards once the program is, while the program's running or after it's stopped running through this saving file.
The biggest problem encountered by the team was that this was the first year of Merlin's hardware team. There were no previous resources, research, or designs to build off of, and on top of this, the team consisted entirely of first, second, and third year undergraduate students. This meant that for us, we had no prior neurotechnology experience, as well as many members had no electronics experience. Therefore, the entire first semester and half of the second semester was entirely dedicated to doing research into neurotechnology, data acquisition, and signal processing, and getting all members to the same base level of knowledge in terms of electronics and circuit design. This large research base did aid our team in the end, allowing for a final design in PCB to be completed and creating a library of knowledge that is available to the future members of the team.
For future iterations of the project, the largest improvements that can be made are in gain, channels, and data transfer through the use of an Arduino Uno. By using an Arduino, the same PCB can use 4 channels instead of just 2. On top of this, once an Arduino is used, the PCB is no longer reliant on the computer's sound card, and therefore doesn't get inputs above 1 volt cutoff. This allows for a larger gain to be used so that the signal can be more easily visualized. Finally, an Arduino can allow for the board to transfer data wirelessly with the use of a Bluetooth module.